Okay. Okay, well, good afternoon, everybody, and thanks again for showing up for another one of our TESS talks. TESS, of course, is our Center for Tropical Environmental and Sustainability Science here at JCU. We're having a real diverse range of different kinds of speakers, and of course, and also when we have an online speaker, we often Ed will have a number of people following this online as well, even through YouTube or Zoom. So this isn't your whole audience here. This is about a third of your audience. Last week we had incredible situation, 151 people. I've never seen anything quite like it. It was a bit of a zoo, but it was interesting. It was nothing boring about it, I'll tell you. Anyway, it's a real pleasure to introduce Ed Pos. I've known Ed for quite a while. For some 5 years, I held this thing called the Prince Bernhard Chair in International Nature Conservation, which funded me to go to the Netherlands for like a month or a couple of trips each year for about a month. And I got to know Ed and various other people in the Netherlands. And I think I was actually helping to supervise Ed's PhD there for a while, but he's moved well beyond that now. So Ed is a theoretical ecologist. He's also a nice guy, and I've known a few theoretical ecologists that weren't the nicest people on the planet, I just have to mention, but he's one that manages to be very quantitative and mathematical and all pull it off with being a really nice person. Ed does obviously theoretical and empirical work, looking at very large data sets, so he's a really serious number cruncher. He's affiliated with Utrecht University in the Netherlands and also Wageningen University in the Netherlands, which are two of the most high-power research institutions in Holland. So anyway, without further ado, we'll turn it over to Ed and thank him very much. What time is it there locally for you, Ed?
It's just 7:04 in the morning.
Oh, that's not so inhumane. Okay, that's not too bad. I thought maybe it was 3 o'clock in the morning or something, so not so bad. Okay, thanks, Ed. Okay.
Sure. All right, so good morning, everyone. I presume everybody can hear me. I see everybody, looking at me, so that's good. Today, I'll talk to you about a quantitative view of ecology. And most of you will be ecologists, I presume, given the theme of these sessions in the test. But I hope to give you a little bit of a different perspective on it. And specifically, I want to give you a perspective that has to do with what we call the maximum information entropy. Now, this might be something you've heard of before, maybe you've heard of entropy before, but then maybe in a thermodynamical point of view, we will all cover this, and I'll end the talk with a kind of brief outlook of what might lie ahead. However, I always start my talks with a picture like this. It's a picture from a field site, and I do that just to remind us of why we're actually doing this work, because as Bill already mentioned, I'm a theoretician, but I also really like to get my boots dirty. So this is a picture from a field station in Ecuador. It's at the Tiputini Research Station located within the Yasuni National Reserve. And it's taken on top of a platform built around a ceiba tree about 45 meters up, which is about 150 feet. And as you can see, this is a great view. I mean, when you look around and you can only see the forest and the biodiversity that's hidden within basically as far as the eye can see, then you realize that the task that we're dealing with and understanding that biodiversity is a truly daunting one. And you quickly also realize that it is pretty much impossible to sample and study all of that rainforest. So to look at all the species, all of their interactions, but there are actually ways that we can circumvent these challenges. And in this talk, I will focus on some of those methods. Now, let's just get started to see what it is that we actually want to do. So what I study is the black box of community ecology. So on the one hand, we have input, which might be anything from community composition to functional traits, environmental conditions that you might have measured, cultural history, spatial data. This is just a random sample. You can do all kinds of things of whatever you are mostly dealing with. And the question that I want to ask is, okay, so if we then look at the output, so if we then observe aggregated values, for example, or distributions that we see, what is it that we get? Well, we get species abundance distributions, maybe. We get spatial and temporal changes in dynamics if we focus on a time series. We get quantitative selection, which in turn determines those species abundances. Maybe there are nonlinear dynamics. And everything that happens within this black box of community ecology then determines the link between the input and the output. And obviously there are two arrows here going back and forth because one also leads to the other. And then one thing I always remind myself as well is like, what do we need and what do we want to do with this? So we want to restore and conserve, for example, ecological systems. So why do we want to understand what's going on in the black box? Well, for example, you want to have more efficient management, right? You want to have concrete handles to maximize the efficiency in the utilization of resources, because we have to face the fact that our resources are not unlimited when it comes to conserving or restoration of these ecological systems. On the other hand, you might also want to be able to do forecasting. What's going to happen in the future? Where should we prioritize? This is just to get the context of what it is that we're doing. And I don't have to tell the people in the audience that understanding how biodiversity works is more important than ever. And I won't go into the details of that, but we all know that biodiversity on a global scale is highly pressurized. All kinds of anthropogenic pressures that are increasing species that we're losing, habitat fragmentation, et cetera, et cetera. You can hold a whole TESS seminar series about this, but we need to have that understanding. And if we look at how we want to generate that understanding, we can first look, let's say, at the left picture. So we see that large tropical rainforest of the Amazon, which is in this case another tower actually in Brazil. And on the right side, you have a local forest, which is in this case in Guyana. And what we want to know is how do we go from that bigger rainforest to the smaller patch of rainforest, and again, vice versa. So what are the processes that are going on, for example, in all of these local communities that then contribute to the larger species community, and then again, vice versa? What determines from those regional species pool, if you would like to call it that, how do we know which of these species end up in the local communities and what their distribution would be? Which species are, for example, most abundant, which are rare? Is this always the case? Does it change from place to place or from time to time? Well, there are obviously a myriad different possibilities of explaining all of these patterns that we observe. But if you put it in a very large spectrum, you might say, well, on the one hand, we have what we call classical ecology, like species evolve for specific niches, and then things like competition and selection actually determine the biodiversity. On the other hand, you might say, well, maybe it's more like neutral theory. Maybe it's more stochastic, probability-driven processes, and then dispersal or dispersal limitation that actually shape the community composition. This is standard in ecology that we tend to think along the lines of either of these categories. And what we would like to do is we would like to have some kind of handles to quantify whether it's more classical or whether it's more neutral. And what I'm going to show you is that first, what I'm going to show you is the necessity actually to have a more quantitative view, to show you the intractability of doing this on such a scale as the Amazon. But I'm also going to show you a specific method of doing this, which is then called the maximum information entropy. But before we do that, it's all about data, because what we can do with any type of model, or whether we want to do any kind of statistical analysis, you need the data. And what Bill already mentioned is that I'm also involved in these large-scale empirical networks, of one of which is the Amazon Tree Diversity Network. And maybe some of you are familiar with it, maybe some of you are not, but this will come back later. So I just wanted to introduce it to you. And I mean, the Amazon is big, right? But major efforts also give major results. And this is a huge network. So this is a network of over 200 authors. If you combine everything, it's over 70 years of work, with the oldest plots dating from before the 1950s, as you can see in this picture here, which is from a very recent paper just last year, in which you see all the dots that are the separate plots that we have in the network. You see the scale. So this is basically the Amazon basin in a schematic picture. And then you see on the right side the legend of the different colors indicating the age time of these plots. Now, these are a single inventory, most of them. So it's not as if this all constitute the time series, but it's just to give you a kind of idea of the sheer effort that it takes. And if you then look at it as dated in 2019, because it's a dynamic network, obviously plots come and go sometimes. So you get 1,946 hectares of inventory, out of which we have identified about 5,000 species to the species level. So 98% is actually, 89%, I'm sorry, is actually identified, which obviously means that we have 11% that we couldn't identify. But for anybody who's ever been in a tropical rainforest, I'd argue that that 89% is actually a pretty decent number. And if you then look at the species, we have about 500 very rare species. Those are the species that just occur with just one individual, for example. And we have 280 hyperdominants. So these are the ridiculously dominant species. Now, if you look at this, and remember, I just wanted to share with you the sheer scale of things that we're doing, is that all of these plots together, they constitute a, you might say, ridiculously small sample. If you consider that the Amazon basin is about 5.5 million square kilometers, and then you take that 1946 hectares, I'm going to show you the first equation in this talk, which is going to be a very simple equation. This adds up to about 0.00035% of surface area that we've actually covered. And then you might ask, what could we do with that? And this is the first quantitative view that I want to show with you, because we can actually do quite a lot with this. We can extrapolate, for example, the species richness and the diversity that we might expect for the entire Amazon if we would have been able to sample it. And we did exactly this in 2020 when we have the bias-corrected richness estimates. And what you see here on the left side is all kinds of different models. So you have the negative binomial, for example, which is the top one. You have the log series, you have Bayesian computation, and then we have an extended log series. Now, I won't go into the detail of what all of these models mean, but what you do see is on the x-axis the estimated species richness. And then we have 3 lines for each of these models. So we have the 2013 data set, which is obviously a long time ago. Then we have the 2013 updated data set, which is taxonomically updated for the, at that time, 2019 newly taxonomic representation of the species. And then we have in 2019 the added plots that we have. So that's about 800 plots that were added compared to the 2013. And then what I want to show you is that all of these methods that you see here, it's actually, relatively speaking, a similar estimation. There was more variation in estimation between the models than we actually had variation between the estimates within a model. So if you look at the taxonomic update of 2013, you see that the species actually decrease a little bit. So if, let's say, we look at the bottom one, the extended log series, you see the 2013 had nearly 18,000 estimates of species. Then you look at the 2013 updated one, it was a lot less. But this has to do with the fact that you lose species, for example, with updated revisions of taxonomy. Maybe some of them are clumped together. And then you see in the 2019, actually, that because we added about 800 plots, then you see that actually the number of species increases a little bit again. But I want you to focus on the fact that these estimates within each method are relatively robust. Obviously, there are differences because you add more plots, but you see that it actually doesn't change that much. So even though we had a relatively, well, not relatively, a almost ridiculously small sample, we're actually quite confident on these numbers of this total number of species. On the right-hand side of this figure, you actually see one of these models, which is the LSE, so it's the extended log series abundance distribution. And I think some of these distributions might be familiar for some of you. And you see on the x-axis the species rank. So the first number is the most abundant. Then you go down the ranks of the second most abundant, third most abundant, etc., etc., etc. And you see here the very famous log series distribution in the dotted gray and red dots, with the red ones being the hyperdominants, and those are the 218 species. And then you see the extension of this, which constitutes an estimated species of 15,874. So let's give or take, let's say it's about 16,000 species. This is a ridiculous number, 16,000 species. For me, being from the Netherlands, I just want to put this in context. I usually do this when I'm giving a talk like this. In the Netherlands, we have about between 30 and 40 native species of tree. Between 30 and 40. Now compare that with the 16,000 that you have in the Amazon. Obviously, it's a lot larger, like than the Netherlands. But even then, the sheer amount of species is a daunting one. Then the question is, how can we figure out for all of those species, what is the distribution? Where do they occur? How abundant are they? What do we expect over time? And on the one hand, you could do that via that classical ecological thinking, right? And as Haeckel already said, ecology is the study of interactions between organisms and their environment. And the classic ecological thinking, it's very intuitive. Like performance varies along some kind of environmental gradient, environmental heterogeneity, it provides a mosaic of potential niches, and then the occurrence is dependent on the ability to compete and survive. Basically, this means we're looking at a deterministic process. And then maybe we go into the field and we do all kinds of measurements. But this quickly unravels, because if you look at this, it's ridiculously complex. I mean, we have salinity, predators, humidity, light, moisture, height, temperature, depth, etc., etc., etc. You need to look at all of these. Well, maybe not all of these, but if you want to have a good understanding, it quickly becomes very complicated. Well, then we say we model it. Like being a theoretician, we like to make models, so surely we could model the real world. Well, even though it might look easy, even just for modeling is difficult. So if we just assume a very simple Lotka-Volterra model, and I'm going to apologize a little bit because there are going to be many equations in this talk, obviously, but I'll talk you through it. Maybe you're familiar with Lotka-Volterra models. So on the left side, you see a time series distribution from 0 to Tn, and then on the y-axis, you see the relative abundance. And all of these lines, they stand for different species, the different colors, so A, B, C, and D. And on the right side, you see the potential interactions that you have. And on the left, in the right-hand side between the A, B, C, and D, you might say, well, all the interactions have the same kind of interaction coefficient. They're all equal. However, we know from experience in the field that this is not the case. So maybe some of these interactions are stronger than others, which is indicated by the dotted lines on the right. In any case, what we need to have is what we call these interaction coefficients, so between each of the species. What we also need is a relative growth rate, which is in the equation in the RS, and we need a kind of carrying capacity, the KS. But if you put all of this together and you say, well, apparently we can't figure it out in the field because it's so complicated, let's make a model because that will make it simpler. But if you put all of this together, it quickly means that you would need S times S plus 2 parameters. Now, remember that we talked about 16,000 species in the Amazon? Let's just look at a system that has 70 species, like a very rich grassland, for example. Maybe some of you have quickly calculated this already. If you just have a plot with 70 species, this would mean you would already need more than 5,000 different parameters. This does not make the world any simpler. So it's a really complicated world out there. It's even, if you think about it, the sheer scale of it, from a quantitative point of view, it is almost impossible. And just to show you that impossibility, and then we're going to delve into the entropy side of it, I want to do a little thought experiment with you. Think about a game of chess. Think if you never heard of this game. So all of you have known chess probably, maybe some of you are very fervent players of chess, but let's just say, let's assume for the sake of hypothetically thinking that you've never heard of this game. You don't know what the rules are. So I want you to close your eyes for a moment and imagine a chessboard with these pieces in the middle of a game. And if you're utterly unfamiliar with the game and you have no clue about the rules, being a scientist, how would you go about figuring out what the rules actually are? Well, you could do it experimentally. You may pick up a piece and then you move it, and then maybe there's a referee saying, no, you can't do that. Or maybe you simulate it and then you say, well, if these are the rules, can I then reproduce this picture of the game that I have? And these are all valid methods of doing this. But if you would calculate the number of possible games that you could have, and I'm going to share that number with you, it's actually something that that Claude Shannon calculated back in the 50s, which also coincidentally, Claude Shannon is the one who brought to us the idea of information theory and the maximum information theory, which we'll talk about later. He calculated that if you take a piece and you consider the fact that on average, it has about 30 legitimate moves. And if you then take into account that if you have 80 plays, then you have 30 to the power of 80. And 30 to the power of 80 is about 10 to the power of 120 possible games. Now, 10 to the power of 120, it's a number we can't almost fathom. But just in comparison, the number of estimated atoms in the observed universe is less. It's 10 to the power of 80. So this immediately shows you the impracticality of solving chess, in this case by brute force. But we're dealing with the same kind of issues in ecology. So it is an incredibly complex world out there. And what we need is that we need something that we can take a look at that complex world and say, okay, so what is it that we actually have in terms of information? And how much information do we need to explain explain and to find the probability distributions that we're looking for, such as, for example, species abundance distributions or spatial distributions of species. But I want you to think in the back of your mind that this quantitative view is not just something that we need to do because it's an interesting new way of going about. It is something that I firmly believe that we need to do because we get more and more data. We have more and more of these collaborative networks, which is great, but it also shows us that there is so much data out there that even though empirical work and experimental work and theoretical work with models, parametric models, have brought us very much, and they're still very valuable if we want to look at like details, we need to have also a broader view. So the question then becomes, how can we deal with this? Well, we are not the only ones that have to deal with this issue. So if you look at complex systems, if we would like to link things like statistical mechanics, information theory, and ecology, if we look at the history of this, then ecologists certainly are not the only ones that dealt with these challenges. In thermodynamics, in the physics side and chemistry side, for example, they've been doing all kinds of work on explaining properties of let's say, gases involving huge amounts of particles. So if we know that a certain container has a certain volume or a certain pressure, what is the most likely distribution of all the particles within that container? Well, on the right side, you see two of these potential distributions. With on the background, you have one that's actually with all the particles in one corner, and the right one, it's particles that are distributed all across the container. And this might ring some bells from the old physics classes, and it has to do with this thing that we call entropy. And I'm going to go into that in a bit. Information theory is something different, which is about quantifying the amount of information that we have, let's say, in a message, or in cases where not all probabilities are equal. Because for the entropy of thermodynamics, you're looking at probabilities that are usually equal, and it's a different kind of entropy. So for the thermodynamical entropy, the idea is that you're interested in the disorder, so quantifying the amount of disorder that you have in the system. In information theory, we're actually interested in quantifying the amount of what we call uncertainty. So if I observe something, what was my expected value that I was hoping to see? So in this sense, if we look at these problems, we're looking at it actually in terms of statistical distributions. And this means that the concept of entropy was born in a sense, but it was in physics and information, and this obviously is not ecology. Now, this has a long history, so it dates back to Laplace and Bernoulli, and then goes all the way down to the 20th century. And then in about 1920, 1930, and later on in 1940, 1950, we see that the idea of information theory really kicks off with publications by Shannon, for example, and others. And we want to make that link between what we mean by uncertainty and what we mean by the idea of getting that information, and then linking it to what we can do with it in ecology. Now, this is a very abstract way of thinking about complex systems, but I will show you an example in a bit that will hopefully make it a little bit more clear. First, before we do that, I want to talk to you about the basic principles of maximum entropy as what we call a statistical inference. So the first part of it is that if you look at this, that any system can be described using what we call micro and macro state variables. So if you look at that physics point of view, you could say, well, the position and momentum of all molecules in the container, that will be the microstate distribution. But we also have these aggregated values, which are like volume or pressure, which is the macrostate variables. If you would look at this from an ecological point of view, then you could say, well, you can either look at the distribution of species abundances, which would be the microstate, and the total number of species, or the total biomass of the system, which then would be the macrostate variable. The second part of this is that you want to find the most likely distribution without including any unwarranted assumptions. And you do this by maximizing what we call the entropy of the probability distribution. You want to describe the microstate that adheres to the given macrostate constraints. And what this does is that the resulting distribution has as much information as is theoretically possible, given the knowledge that you have, and nothing else. Now, why is this important? It's important because we could also develop methods that create these probability distributions, derive the probability distributions, for example, with these complicated models that I showed you in the beginning. Parameterize all of these models, you get all kinds of knobs that you can turn on the system, and then you do that just as long, and then you get the distribution, you say, well, this is it. But we've also shown that there are many ways that you can actually model the exact same distribution. So how then would you know that you actually have the correct parameterization of your model? The idea of maximum entropy is that you say, I'm not going to do that. So the prior one would be a bottom up. You have an idea about the mechanisms. I'm going to put that in a model, and then I'm going to see if I can get the distribution out of it. Maxent is actually a top down. You say, well, I have observed a certain distribution. I have observed certain macro state variables. How can then I calculate the most likely distribution that still adheres to those macroscopic constraints? It doesn't involve or assume any explicit mechanisms about what is driving this distribution. And this might sound very easy to a certain extent, but it's complicated, and it's a little bit of an abstract thinking process. So I just want to look at an example with you. And this is a really great example. And for people who are more interested in this, I really highly advise looking at a YouTube series. It's called Maximum-Entropy Tutorial. It was done by Professor Simon Dedeo of the Santa Fe Complexity Explorer series. And it explains very clearly what this idea of maximization is. Now, I just want to give you a brief summary here. If we go into the field and we measure, well, we could look at, let's say, a local community A, or maybe a local community B, C, and D as well. So these are all the local communities. And together, they form the regional community. So the regional species pool, for example, is the aggregated kind of clumped series of all of these local communities together. And this is what we usually do in ecology. If you look at all these plots that we have in the Amazon Tree Diversity Network, then they all add up to the regional community, with which we then can do all kinds of calculations. Now, what do we measure in the field? We measure individuals. We measure all the species that we have. We measure their abundance. We might measure their cover. We might measure all kinds of abiotic data. We might measure functional traits. And you can go on and on and on. And usually it looks something like this, right? So you have a contingency table with these local communities, A, B, C, and D. And they have these species. I just put 10 species here, but let's say you have N number of species or R number of species for the ranks that you have. And then you can calculate, you observe all the different abundances of these species, and you do that for all communities. So far, so good. But then the question that we might want to ask ourselves is, well, if we look at, let's say, community A, and we would make a rank abundance distribution like the one that we saw in the beginning of this extended log series, I could look at the abundances. I can derive that distribution from the field. So let's say the first ranking species had 25 individuals. Then the next one had 24 individuals, etc., etc. Then what is the probability of finding a species that actually has N individuals? In other words, I want to recreate this rank abundance distribution, but I want to do that in the most unbiased way without involving any type of mechanism. So the question then becomes, how can we explain the pattern of abundance? Well, I just already explained it. We could do this with simulations. Like, do we get the same distribution? We can do this with complex models. Do we get the same distribution? But we already know now from these examples that this is highly complex and it's intractable. So we employ the maximum entropy principle, which is what I just explained, a top-down approach based on the data, without any other assumption about underlying mechanisms, but with what I call limitations that we observed. So if you look at that same distribution again, PA of N, and we look at the first ranking, it's 25 individuals, the second one is 24. And if I look at that whole distribution, I could say, well, what is it that we do know about this? Well, we maybe see that the average number of individuals is 4. This is just a hypothetical example. But let's say that the average number of individuals for a species is 4. I could then try to figure out a way to maximize the uncertainty that I have about the distribution, but it has to adhere to the fact that it has an average of 4 individuals. Well, there are still many distributions that could potentially fit this constraint. The left one does, but the right one does as well. So on the left side, you have all the ranks and you have the abundances. And let's say that hypothetically, this is the abundance distribution that we find, and it has an average of 4. The right one also has an average of 4. So which is the right one to pick? And here's where the entropy comes in. Because what we do is we maximize the uncertainty of the distribution. In other words, we maximize what we call the Shannon entropy. And the Shannon entropy here is given by the minus summation of all these different ranks in this case, and we calculate the pi, so the probability, times the log of the probability. And this is actually something that's probably familiar for a lot of you, because this is also what we use in ecology when we look at the Shannon diversity. So on the right side, you see actually this uniform distribution, which in terms of the Shannon entropy, in terms of the diversity index, you would call the most abundant, the most diverse one. All the different species have the same abundance. The link with uncertainty comes then from, if I would pick a random species from this distribution, I would have no a priori information on which of the species it actually would be, because they're all equally abundant. So I've maximized, in this case, I've maximized my uncertainty. If I then would look at how to do these calculations, and I just made a quick example from this tutorial, and you would do these calculations, you would actually see that if you do this, and let's say that the pink one here is actually what we have observed, then the white one would be what the outcome of the distribution is if you would only take into account the average abundance of species. Now, what you see in this case is that Maxent, you would say, does not predict it very well. And that makes sense, because why would you expect that having only the constraint of the average number of species would be a very good approximation of a very strict constraint? In this case, you would see that having just the average number of 4, it will overpredict those intermediate species. So you would say, what use is this? Well, I could also show you that if I include more constraints, let's say on the average metabolic energy distribution, then I would get patterns that are much more alike what I see in the field. It is actually possible to show that you can derive Fisher's log series. So this is just a toy example. But if we would have more information, so if we would have more information on, let's say, functional traits, do we get a better prediction? And then the question is, how can we apply that principle to actual cases? So this is just a very quick overview of what it means if we say we maximize the uncertainty. But what I want you to get from this is that we maximize the uncertainty to also minimize the bias that we have about the system. We are only looking at the data that we have, and by the means of the maximization of this entropy and the mathematical calculations behind it, we can actually derive the probability distribution of what we would expect. So what is the probability for a species to have n individuals, given only the information that we have, with the end result of the distribution adhering to the observed state variables, in this case, for example, that average of 4. And if I then do this for the field data, I might say, well, I'm interested in predicting these distributions, and I'm taking into account, let's say, the total number of species, or the total number of individuals, or maybe the ratio between them, or maybe the total biomass, or maybe, well, you can go on and on and on. And I hope that you can now link that with what we find in the field versus what it is that we're trying to predict, and why this method is actually very capable of creating a very unbiased prediction. And then from that, we can derive all kinds of ideas and hypotheses about the mechanisms that are driving this. Because remember, there are no explicit mechanisms within this framework, but we can derive them. And I'm going to show you an example of how we do this. So remember that Amazon Tree Diversity Network. So we go out into the field, and then we're going to find out what are the species in the distributions. And I always use this picture on the left side because on the one hand, it shows you what it's like to be out there. And for those who are wondering, yes, that is me smelling a tree to find out which kind of family it is in this case. And then on the right side, we have all of this data. And then what we try to do is we employ this principle of maximum entropy. And I'm going to use a very specific framework of maximum entropy because there are different frameworks out there. This is the community assembly by trait selection. And this looks a little bit daunting, but I'm going to take you through it. So on the top left side, we have that same contingency table with site A, all B, all through X with the different species. And then the table below shows you the functional traits that we know. So for each species, we have trait 1 through trait J. And then what we're trying to do is we're trying to combine these things. And I'm hoping that my laser pointer is going to work. So I'm hoping everybody can see the laser pointer. If you look at this equation on the top here, it's the same equation that we saw just now, the pi times the logarithm of pi, but with an added aspect is I divide by qi. And qi here is the regional species pool. Because if anything else, if there is no functional trait selection, if there's no trait-based functional selection, then you might expect that the regional species pool of all of those communities provides you with a good prediction of what you would locally find. So what we're actually calculating here is the relative entropy. And then what you see in the second row here are the constraints that we're taking into account. So remember that average of 4. Well, here it's not the average of 4 that we're trying, not the average abundance, but I'm taking into account what we call the community weighted means. So for any local community, the prediction that I'm going to make of the species and their abundances, I can recalculate the community weighted mean of a functional trait, say the community weighted mean of wood density, and whatever the prediction that I'm going to make from the Maxent framework, it has to adhere to that same state variable of this community weighted mean that I've observed. And then the other equations are to calculate the differences that you see in the predictions using different models, because what we do here in the models is actually a 4-step model. So step 1 is we say, well, what if we assume a uniform distribution for the regional species pool? So all the species would have the same abundance. And then we assume as well a random distribution of traits. So I'm going to shuffle all of these. So if there is any link, I'm going to take it away. And I do this to create what we call the model bias. What kind of information is there within the data just because there is information in the data? The second step is I used actually the observed distribution of the source population, so the observed regional species, but I'm still going to shuffle the distribution of the functional traits. So this is the model bias plus the regional species distribution, which is actually something we use to, for example, estimate the importance of a meta-community. The third step is then, well, I'm going to do it the other way around. I'm going to use a uniform distribution of the regional source population, but now I'm going to use the observed functional traits. And then the last, which probably something you already guessed, is I'm going to put everything together. I'm going to use the observed distribution of the source population, and I'm going to use the observed functional traits across the species. And for every step, I'm continuously redoing all of these calculations to get these predictions and to fit the predictions to what I've observed. Now, what you would expect is that if the regional abundances give me any kind of information about what I might expect locally, then my prediction will be pretty good with what I've observed in the field. Or if my functional traits have anything to do with what I've observed in the field, then I would expect that that would give me information, and the combination as well with something in between. Now, I'm not going to go into the exact details or the exact calculation. I just want to show you that if I use the uniform distribution of the regional species pool and I combine this with the observed functional traits, I only get a R² between the observed and predicted relative abundances of about 0.19. Now, this might not seem very high, but you have to take into account that we're looking at a huge data set. So this is the Amazon Tree Diversity Network data set that you just saw. And in terms of ecology, this, let's say, 0.2 R² is actually pretty decent. If you look then at the fourth step, which we include both the selection and the distribution, the regional species distribution, it actually increases. So it goes to 0.38. So we could explain a good proportion of the variation in what we see in observed abundances using just the Maximum-Entropy framework. And what we can do with this is we can actually quantify the trait selection, the dispersal effect, the joint effect, and any unexplained effects. And the unexplained effects is something that you might consider that you couldn't link to either the regional abundance or to the functional traits. And this might be due to stochastic processes, but it might also mean that we haven't included the right constraints. So even the fact that the model cannot explain what we see gives us information of maybe what we should look for. And in addition, we can actually calculate the contribution of each of these functional traits to the observed patterns. Now, what I want to show you is some quick results. So if you look at these trait effects, the meta-community effects, so the trait effects, remember, is just the trait effects. So what information do the traits give me? And what information does the regional abundance give me? And what is the joint effect? And then what is the unexplained effect? And the different colors here, they stand for the different forest types. So the blue is, for instance, Igapo, which is flooded forest, specifically flooded forest. We have potsol forest, the yellow. We have swamp forests, and we have different terra firma forests, the brown sand soil forest. And then the purple is Vargia, which is also a flood forest, but a different type of flood forest. And what you see here is that we did this on genus level taxonomy, so not on the species level. And the fact is that we don't have the information yet on all the functional traits for the species level. So this is genus level selection that we're looking at. And you see that the trait effects are very low. So the trait effects are very low in comparison with the pure meta-community effects. The joint effects and the unexplained effects then show that the joint effects of both the meta-community and the pure trait is lower than the pure meta-community effects. And the unexplained effects are still relatively high. Now you might think, what is it that we can then do with this? But what we show is that it's very consistent. So if we look at the pure trait effects and then we delve a little bit deeper into the details, we can look at actually the functional traits that are selected for. So on the left side, the very left one, we have wood density and we have seed mass class. Next, we have the SLA, and then we have all kinds of different functional traits. I want to show you two specific ones, which is this one, the nitrogen leaf content and the phosphorus leaf content of the leaves. And if you look at these yellow bars, these are belonging to the potsol soils. So these are relatively nutrient poor. And if you look at the y-axis, this is called the lambda value. And the lambda value is something that comes from the calculations of the maximum entropy, and it quantifies how much the change of prediction is with respect to this functional trait. So if it's negative, you might interpret this as it is selected against. So when this is negative, it is related to a lower abundance, right? So what you see is here actually that a high leaf nitrogen content is associated with lower abundances on these potsol soils, which mechanistically makes sense, right? And if you look at all of these functional traits, for the majority of them, we notice that it is very much in line with what we would expect, mechanistically speaking. So wood density, for example, on the very left, you see that for some of these terra firma forests, it's actually very positively related, which is also something we would expect. And the cool thing is here, without going into the strict details, is that we discovered these patterns without implying any kind of mechanism in our model. Because I could have also put it into a model. I could have said any species with a high leaf nitrogen content has a lower success rate on the potsol soils. But what would be my assumption for doing that? It would be a hypothesis and I could test it, but I would have no clear idea of that bias that I would have introduced. But the maximum entropy framework actually derives this without including any bias. And I think that that's just a very cool result. Now, if we look at the dispersal effect, you also want to know what is the importance of the meta community. And remember that we included the regional prior. So we included the regional meta community abundances as a kind of comparison. And what we did here, which I think was a pretty cool idea, is that we increase this iteratively. So if you look at the left side, you see this picture of the Amazon, and then you see all of these plots, and then we focus on the one plot. And then for the first iteration, we used only the plots in the very near vicinity. So let's say hypothetically 50 kilometers. Then that is the regional species pool. And then from the next iteration, we increased it. We made it a circle radius of 100 kilometers, 150 kilometers. And on the right-hand side, you see what that means if you would increase it. And the idea behind this is that if you have the first iteration, then probably the species that occur in the neighborhood are the same ones that occur in the local plot. So you would expect that the meta-community effect would be very strong. But if you increase it all the way up to the entire Amazon, then you would expect it to decrease. So with further distance, you would expect the importance of the regional species pool to decrease. And remember, we don't put any mechanism in this. This is just observed data. And then if we look at this, at the importance of the meta-community, and you see on the x-axis here the distance from the focal plot, starting from 100 to 3,600 kilometers, then we see the pure meta-community effect on the y-axis, and you see actually that it decreases. So it decreases relatively quickly, and then it stabilizes. So for the first 500 kilometers, regardless of forest type, because the different colors here again constitute the different forest types, you see that it decreases. The dotted line here indicates the proportion of all plots that we included, because obviously for the first iterations there will be very few plots, and then all the way down to the end you will have all the plots included. And then you see that once you pass that 500 to 700 kilometer boundary, it doesn't change anymore. So these are probably the species that, or the genera I should say, that occurred almost throughout the Amazon, because we're looking at genus level taxonomy. But to combine this, we see that for the functional traits, we see that we find relationships between these lambda values that quantify the associated change with the associated change in the functional trait, whether that's positive or negative. And we see the meta-community importance, and they both show us what we would expect based on our ecological theory. But now we can quantify that effect, and we did it without including any bias, without including any unwarranted a priori assumptions for which we had no a priori support other than our expertise. This is just a very simple example, well, maybe not simple, but it's an example of how we can apply the maximum entropy to a large-scale data set here. And the next slide that I'm going to show you is from John Hart and Golan Amos. And it's a very daunting slide, but don't look at all the equations because there are a lot of equations in there. It just shows you the framework of what you can do. So if you look at this max end, you can derive what we call the ecological structure function, which is the basic framework of the max end that John Hart, for example, derived. And we have the species level spatial distribution. But look at all the things that they were able to derive from this. So they can look at, for example, the distribution of abundance over species. They can find an equation of state. They can find the distribution of metabolic rates over the individuals, interspecific metabolic rate distribution, endemic area relationships, species area relationships, abundancy occupancy relationships, etc., etc. So this very, very clear idea of this statistical inference with these joint distributions that you see here above in the ecological structure function, that you say, I look at the number of individuals, the metabolic energy, given the state variables of the number of species, the number of individuals, and the total metabolic energy, gives me all of these distributions without including any explicit mechanism. And I think that this is just a very cool result that you can use ideas from other disciplines to give us understanding of what we see in the field. Now, I'm going to show you just one more example of a challenge that we're now dealing with. And if we look at ecosystems, for those of you who noticed that the Maxent idea or the Maxent framework, the way that we use it is based around equilibrium. So it's based around the idea that we have equilibrium values. So what actually Hart already told us in communications biology just 2 years ago is, and I quote, we might more generally expect the predictions of a top-down Maxent approach to fail under ecological disturbances that sufficiently alter the fitness landscape. Because what happens is those state variables that we're looking at, so these maybe community-weighted mean state variables of the functional traits or the number of species, they change. They're dynamic. They're not static. So if you look through time here, for example, and you look at the species abundances, they might change through time. So all of these different species here, they might change through time. And I can put this in a different view in what we call an attractor. And if you then have Z, Y, and X as 3 species, I can reconstitute an attractor. And these lines, they give me the same kind of lines that you see on the left side figure. And these are the types of manifolds, as we call them, that constitute the dynamics of these systems. anybody working in ecological systems, and especially looking at ecological systems that are disturbed, will know that it is dynamic. It is not static. We see this type of pattern. So then the question becomes, how do we deal with that? How can we go from this maximum entropy framework that is applicable in equilibrium states, and how can we use that in a dynamic variant? Well, this is an ongoing topic, and it's really a frontier of what we're currently working with, also with my group. And there have been some contributions. So the first I want to show you is what's called dynamic meat. And meat is the maximum entropy theory of ecology. And what dynamic does, it actually includes what we call transition functions. Now, I'm not going to go into the details, but here you see that they include transition functions. And these transition functions are mechanistic functions, but they're updated within the system of maximum entropy. So it's a kind of marriage between hybrid theory, is what they called it themselves. And I quote from the paper, is that dynamic is a hybrid theory based upon both the logic of the maximum procedure, but also the explicit mechanistic assumptions about the drivers of change. And these transition functions describe demographic, ontogenetic growth, migration, extinction, speciation. And what it does is actually shows you it's capable of capturing the dynamics. But this does include these mechanistic transition functions. This is really on the forefront. So this is published just in 2021, and this is really recent stuff that people are working on now to see if we can develop more elegant ways of also including these mechanistic approaches, but maybe also looking at approaches that don't include these transition functions. One other way is to do it is to look at what's called maximum caliber. And maximum caliber is a different way of looking at it. So whereas maxent on the left side is about equilibria, and it is to derive the most unbiased microscopic distribution at that equilibrium, max caliber, which is actually something that was already introduced a long time ago, is concerned with the probabilities of pathways. So all of these spaghetti strings that you're seeing here, they are pathways of how it changes through time. So if you look at all the possible histories, which is the most likely history given the dynamical constraints that you have, and how can we use that to maybe predict into the future what we might expect? So instead of looking for distributions that fit equilibrium state variables, you look at dynamical constraints and you look at the trajectories that these have. Now, on the right-hand side, it's called dynamic maximum entropy, which is from this specific paper that was in PLOS Computational Biology of 2021. And they did a kind of hybrid idea of an intermediate solution involving the simplification of a deterministic dynamical system in which they used the so-called Fokker-Planck equations. I won't go into the details of that. That's a whole different lecture, I guess. But it's a partial differential equation that describes the time evolution of a probability density function. And this is also a hybrid kind of idea to see if we can find a transition between that maximum entropy, so the static approximation, to a more dynamical approximation. Now, I can imagine that this is all very abstract and very complicated as well, but I hope to get across the message that a quantitative view of ecology is not only necessary, but it is also a very valuable way because it can also feed into all kinds of subsequent work. So what we find from these quantitative methods can feed into, let's say, new empirical studies, new experimental studies, or it can feed into new theoretical studies. So it's a kind of circle, you might say, in which we have data, we try to get the most unbiased prediction of what that means, and then that feed into different disciplines. So it's an added method to the toolbox of ecologists, not to replace, but I think expand our capabilities. And what I just want to do is I want to end again my talk here today with a slide, which I always use when I end. It's just to get us back to the reason why we're actually doing this. And they end with a quote by a physicist called Richard Feynman, who talked about the inconceivable nature of nature. So this brings us back from the equations of the blackboard to the purpose of our endeavors, and that is to see if we can develop methods and means to actually quantify the things that we see out there, like all of these species. Thank you very much.
Does anybody have any questions?
What's that, sorry?
Does anybody have any questions?
Yeah, I do. Yeah. Hey, Ed, thanks very much for that. Really interesting. And it won't surprise you to hear that quite a lot of that sort of on the fringes of what I think people here are used to doing. We don't have a theoretical ecology course, you know, as a subject offered here. So it's some of that's a little heavy hitting. I was wondering, as you were talking, I was feeling like it almost sounded like a lot of the stuff was sort of Hubble neutral theory in the terms of the concept. I'm just curious to know, do you see yourself very much as sort of seeing the world the way Steve Hubble does in terms of, what he does and this neutral theory, or are you kind of going off in a different direction from that?
I think that's a very good question, and I think that it's a bit of a different direction. So my graduate thesis was actually on the neutral theory, and to see if we can make it more realistic, so to say. So the neutral theory obviously assumes ecological equivalence. What the Maxent framework does is to say, I actually make no assumptions a priori. So what Hubble said was that if we assume that there are no differences and we just have that dispersal mass effect, how much would that actually already explain? And then anything we can't explain, we have to adhere to things like the classical ecology side of things that we know or that we assume that we know about the system. So one of the things that we showed, for example, was that the neutral theory for the Amazon tree diversity network data, it was incapable of explaining the most dominant species. It underpredicted those. So we knew from that framework that there must be something that these species are doing that allows them to be more dominant than what ecological equivalence would predict, right? So in that sense, it might be kind of similar, that you can use the framework of neutral theory to see what it is you can't explain. But I would argue that Maxent is a much more flexible method of doing so, because it involves no assumptions at all, a priori. If that answers the question.
Yeah. Well, yeah. I mean, again, I confess I'm sort of on the. I actually read Steve Hubble's book, so some time ago I had a lot of that in my head, but it's been a while. Sorry, there's another question I was going to ask you. Let's see, Maxent. Oh yeah, you were talking about Maxent. Is that the Hugh Possingham model, or is that something else that they're talking about here? Because they do a lot of work with modeling species distributions. Is that what they developed, the Possingham?
I'm not sure I'm familiar with that. Could you, what is that again?
Does anybody remember Hubble? They've got a model for predicting species distributions, and they use it a lot. And I was thinking, it's not Maxent then. Yeah, I'm just trying to remember what the name of the model is, but they use it for a lot of stuff like climate modeling, things like that. Species envelope modeling, that type of thing. Yeah.
Well, it could be. So what you do see, and that maybe is interesting because maybe some of you are familiar with like species distribution models, like the very pretty maps that you see of species ranges and the occurrences that you have. And Phillips et al. Actually introduced the Maxent. So that's what many people in ecology, when you're talking about Maxent, and if they're familiar with it, they usually mean the species distribution modeling part of it. But the engine behind that is actually the framework that I just told you about. So it uses the same kind of methods. So Maxent, in that sense, there is more than meets the eye, but it's also more. It's being used in a sense. Yeah.
Okay.
Hi, Edwin. My area is actually in education and communication. So I was just wondering, you have all these like really fantastic maths, but how does it actually apply in conditions like where you're getting very rapid environmental change, like you've got a heat jump on, or you get, bulldozers through or something? How does the math work then?
That's a very good question. So as I showed in the last few slides, is that this is something that's being worked on at the moment, right? Because these massive changes, these abrupt changes, so the bulldozer, but also like things like critical transitions, right? If you look at things like climate change and you look at critical transitions, or maybe you have overgrazing, or all of these kinds of processes that we know that we're going on, this is where the maxent fails at the moment. But the interesting thing is that the failure actually gives us information, because the failure of the prediction tells us what is missing. So it tells us something about we're not predicting this right. So there's something going on. And obviously, if you're looking at a system that has just been bulldozed over, you don't need Maxent to tell you that something's changed, right? I mean, you can see that. But what if it's more under the hood? So what if things are changing that you're not seeing explicitly? So let's say invasive species came in and they're changing the abundance distribution, but it's not something you could see a priori just by looking into the field. We do the predictions and then you see, wait a minute, they're not predicting correctly. So there's a deviation here. And one of those things that I showed you, which is actually a nice example here, is that equation of state. So one of the things that John Hart et al. Derived from this maximum entropy framework is very cool. It's called the equation, an ecological analog of the equation of state. And an equation of state in physics is this relationship between these state variables like pressure, volume, temperature. And they've shown that they can derive an ecological analog of the equation of state looking at predictions from Maxent when it comes to the biomass and the number of species, for example. And what you then see if you apply this, and they've shown this as well across taxonomic groups, so from arthropods to mammals to trees, you get this equation of state, but you also see deviations. And this is where the interesting part is, because the deviations tell you that that equilibrium state assumption is being violated. So there's actually something going on that you didn't anticipate, but the failure is actually something that gives you that information. Obviously, it doesn't give you the answer, but it gives you information that something is going wrong in terms of the prediction. And that gives you the handles to look into this in more detail. I hope that answers your question.
Yeah, thank you.
Any other questions? Well, Ed, thank you very much. We really appreciate it. And it's nice of you to come to us such a long distance away. And that was an extremely lucid, clear, I think you presented that about as clearly as it could be presented. I still haven't confessed and swing. I'm probably going to wake up in the middle of the night screaming with mathematical symbols in my head. But still, I think you did a really good job there, Ed, and we really appreciate it. And thank you for talking to us about something that we don't hear a lot about these days, which is the realm of theoretical ecology. So thanks a lot, Ed. Appreciate it.
You're welcome.